All right, so if we look at this diagram here on the first slide, so here you've got two circles, and each of those circles represents a mass. Now, both circles have the same mass. Now, if you look at the two arrows, the one on the right has a bigger area, and the bigger the area represents the bigger the force. So, although both of them have the same mass, and the one on the right has a bigger area, that would suggest that the force is stronger. Now, if these two objects were placed on a planet, let's just say, which of those objects, which of those planets will have the strongest gravitational field strength? So the one with the strongest gravitational field strength will exert a force on the object with a bigger force. So the one with the bigger arrow will have a stronger gravitational field strength, because the obviously the bigger the area of the force, the bigger the area of the arrow suggests the bigger the force. So the one on the right is it means that it has a stronger gravitational field strength. If we look at part number 2, where it says number 2, let's define gravitational field strength. So gravitational field strength, G, is the force per unit mass on a small test mass placed in a field. So the equation for gravitational field strength is G is equal to F divided by m, where F is measured in newtons and mass is measured in kilograms. So the unit for G is newtons per kilogram. And if we look at F equals ma, it is exactly the same formula. You're just rearranging for A. So rearranging for A, you end up with F is equal A is equal to F divided by m. So what is the other unit for G? We know that one of the units for G is newtons per kilogram. You can say that the other unit for G will be meters per second squared. If we look at 3, where it says 3, there are 3 objects. Each of them have a mass m1. The other one has a mass m2. The other one has a mass m3. For this diagram, what we're trying to show is that all masses create a gravitational field. So if we look at object, the first object, the square, the mass of the square has a mass m1. If a small test object is outside the square, it would experience a force F1, because the object that has mass m1 has created a gravitational field, and so therefore it is attracted towards the center of the object that has mass m1. If you look at the object, if you look at the pentagon with mass of m2, an object that is placed outside the mass will experience a force F2. Similarly, with the circle, let's just say that it has a mass m3. An object placed outside that field, outside the object, will experience a force F3. However, this is just focusing on the individual masses. If you were to calculate, if all of those 3 objects were in space and an object were placed somewhere around where there are 3 objects close by, then the force exerted on that object will be the vector sum of all those forces, F1 plus F2 plus F3, but it won't be represented by the same diagram. If you look at 4, the one that says 4, G is equal to F divided by m. So let's just go back to what it means, what those terms mean. In this case, F is the force exerted by the mass that is in the gravitational field, and m is the mass in the gravitational field. And so to work out G, you would just do F divided by m. Let's look at the second diagram. So the second diagram, radial and equipotential. Let's have a look at the definition radial. So the word radial, where it says in the middle of the slide, a symmetrical field that diminishes with distance from the center, where the lines spread out from the center in all directions. So the word radial is different from the word uniform. So if you look at the diagram where it says uniform gravitational field, the word uniform means that the gravitational field lines are parallel to each other, and they're equidistant from each other. So if you look at the one on the right hand side, the top right, if you look at radial and uniform, they have different meanings. So radial is not uniform. So radial means that it is a symmetrical field that diminishes with distance from the center, where the lines are spread out from the center in all directions. If you look at the one on the bottom left, the direction of a force on a mass placed in the field is shown, and you can see that the arrows are always pointing towards the center of the mass. So in this case, it is always attractive. The field is not uniform because you can see that they are coming radially outwards from the center of the mass. The field is not uniform. The field lines are never parallel or equally spaced. So as you move away from the object, the strength of the field reduces as you go away from the center of the mass. And if you look on the right hand side, just going back to that equation, the gravitational field strength is force per unit mass. So what this diagram shows is that the one that has a bigger mass, in this case the one with the bigger circle, the bigger area, that object with the bigger circle will exert a force F on the object with mass small m. And so to work out the gravitational field strength would be F divided by m. If you look at the first slide, the weight is the force experienced on the mass in a gravitational field. So the mass that is creating the gravitational field, that will exert a force on that mass, and that force is called weight. And it is always attractive, meaning that weight, due to the gravitational field, the force acts towards the center of the object that is producing the field. So that's why we say small. We say small because then it will not affect the gravitational field of the bigger object. Because if the mass was much bigger than the mass that is creating the gravitational field, then it would be confusing. So the reason why we say small mass is so then it does not influence the gravitational field strength of the object that has the bigger mass, because the one that has the bigger mass is the one that's actually producing the field. Okay, so going back to radial, radial is a symmetrical field that diminishes with distance from the center, where the lines spread out from the center in all directions. So if you look at the diagram, the one with the Earth and the red arrows pointing towards the center of the Earth, that is radial, and it is always attractive, meaning that the force is always towards the center of the Earth. And an object that is placed on the Earth will experience a force acting towards the center of the Earth. If we go to the diagram on the right where there's a moon and the Earth, the moon is attracted towards the center of the Earth because the mass of the Earth is much bigger than the mass of the moon, so the moon will go towards the Earth. But why does it go in orbit? Now, the reason why it's going in orbit is that the moon is also moving at a speed. So although the moon is moving with a certain speed, it is attracted towards the center of the Earth. So you can say that the moon is falling, but it is falling parallel to the center of the Earth. So in this case, you can say that the moon is falling towards the center of the Earth, but it never goes towards the center of the Earth because the forces are, the forces are not balanced, because it is accelerating. But the reason why it's going towards, the reason why it's going in orbit, because the moon is moving at a certain speed. And if we look at the last slide, equipotential lines are always perpendicular to the gravitational field. In 3 dimensions, the lines form equipotential surfaces. The equipotential lines are therefore circles, and a sphere centered on a mass is an equipotential surface for a 3-dimensional space. The definition for a gravitational field is a region in which objects with mass experience a force. If you remember an electric field, it is a region of space where charged objects will experience a force. Radial. Again, radial means imaginary lines coming from the center of the object coming outwards in all directions. So if we look at the diagram at the bottom of the slide, here it is uniform. So the word uniform means that the lines of force are parallel and equidistant. Parallel means that the distance between them never change. I suppose the word parallel implies equidistant. This is on, if you were on a flat space. So if it was flat and you've got lines that are parallel, then they will be equidistant. The gravitational field strength does not change because they are parallel and equidistant. If you look at the word radial, the lines of force are not parallel and not equidistant because the lines of force are concentrated at the center and it spreads outwards in all directions. So the distance between the lines of force is increased away from the center. Let's look at diagram 3. So all these 3 diagrams represents three different types of masses, and all masses create a gravitational field. So if there is an object with mass m1, then if an object is placed outside that object, let's just say a small mass, then it will experience a force of F1 because the mass that has a mass, because the object that has a mass m1 will create a gravitational field, and a small test object would experience a force F1. If you look at m2, the mass of that pentagon has a mass m2. If a small test object is placed outside the object with m2, it would experience a force F2. And similarly for an object with mass m3, if you have a small test object